This conference will now be recorded.
Dear students, last class I explained this wedge failure of stability analysis of finite side slopes. Last class I explained this procedure. Here we are discussing the stability analysis of finite side slopes. In the previous classes I explained stability analysis of infinite side slopes. After that, last class we started the stability analysis of finite side slopes. Before going to construct this finite side slope, we know that we have the finite side slopes in embankments, canals, and also earth dams. The sides of the embankment is a finite side slope. The sides of the canal is a finite side slope. The sides of the earth dam is also finite side slope. Before going to construct the embankment, canal, and also earth dam, first we must check the stability of the finite side slope in those structures. The stability analysis of finite side slope is entirely the paper work. So please listen everyone. The stability analysis of finite side slope is done on the graph sheet. What is the procedure? What is the procedure in that stability analysis of finite side slope? You are all in the beginning of this side slopes stability analysis. You are very fresh to these concepts. So please understand the procedure clearly. Then you will get the experience in this stability analysis of finite side slopes. So please listen everyone. What is the procedure normally adopted in the stability analysis of finite side slopes? The stability analysis of finite side slope is done on a graph sheet. In that graph sheet, first we prepare the plan of embankment, canal, or the earth dam on the graph sheet. So we prepare the plan of the embankment or the canal or the earth dam on the graph sheet, including the side slope. Along with the side slope, we prepare the plan of the embankment, the canal, and also the earth dam on the sheet. So this is the plan of an embankment. So including this earth slope, prepare this plan on the graph sheet. Now in this diagram, AB is the finite side slope. We are going to check the stability of this finite side slope. Stability means in the finite side slope, stability means in future about which failure surface this side slope is subjected to failure. In future, after construction, if and all the failure happens, in the worst conditions, if and all the failure happens, we know that this finite side slope subjected to failure because of number of forces, because of this gravitational force, because of the seepage flow of water, because of sudden drawdown in the water level, and because of erosion, because of earthquakes. This side slope may subjected to failure in the future. In the finite side slope stability analysis, we are going to locate what is the probable failure plane inside this embankment. What is the location of the failure plane in the embankment or the earth dam or the canal? About that failure plane, this side slope may subjected to failure. So the location of the stability analysis of finite side slope is the location of the failure plane inside this structure. About that failure plane, there is a failure of this finite side slope. That is the stability analysis of finite side slope. So in the stability analysis of finite side slope, we are going to find out where is the failure surface. Where is the failure surface in this in this structure? This may be earth dam, canal, or embankment. Where is this failure surface in this structure, so that in future the side surface this finite soil surface subjected to failure about that surface. In order to locate that failure surface in this structure, we are using the procedure, some procedure. I am going to explain that procedure in this discussion. So in the wedge failure of finite soil slope, I am going to explain you the procedure to locate, to find out the failure surface inside the structure. And in this discussion, we assume this failure surface is a wedge failure. You know that the finite soil slope subjected to two types of failures: rotational failure, actually three types of failures: rotational failure, combined failure, and also wedge failure. Sometimes this failure, this soil surface, soil slope, sometimes this soil slope subjected to wedge failure along this plane failure surface. In this discussion, I am going to explain you where is this location of this failure surface in this structure, so that in future this finite soil slope may subjected to failure. In order to locate this failure surface, first prepare the plan of structure on the graph sheet, including this finite soil slope. Prepare that plan on the graph sheet. So here AB is the finite soil slope of the structure, making an angle I with horizontal. After the preparation of this plan on the graph sheet, once this plan is prepared on the graph sheet, in that graph sheet, according to convenient scale, 1 centimeter is equal to 10 meters or 1 centimeter is equal to 20 meters scale, prepare this plan on the graph sheet. Once this plan is prepared on the graph sheet, in that graph sheet, first take one failure surface, one wedge failure surface like AD. So we consider one arbitrary, this is not the accurate, one failure surface AD in the graph sheet. Now we are going to check, we are going to discuss what is the factor of safety of this failure soil surface about this failure surface AD. So in the graph sheet, first we consider one failure surface AD in the graph sheet. Now we are going to discuss about this failure surface AD, what is the factor of safety of this finite soil slope. To find out the factor of safety of the finite soil slope about this failure surface AD, first consider this soil portion ABD in the graph sheet. This is the soil portion ABD in the graph sheet. Since this is the portion of soil, this ABD is in the graph sheet, it is a triangle. Measure the height of the triangle in the graph sheet. This is the height of the triangle in the graph sheet. This is the base of the triangle BD. By knowing this height of the triangle, base of the triangle, calculate the area of this ABD triangle. According to scale, calculate the area. Take the unit thickness in the perpendicular direction, 1 meter thickness. Take the unit thickness. Then find out the volume of this ABD soil portion. Volume is equal to area into unit thickness. You know this bulk unit weight of this soil. Bulk unit weight is known from the observations, field observations. We know this bulk unit weight. By knowing the volume and the bulk unit weight, calculate the weight of the soil ABD, W. Find out the weight of the soil ABD. I am explaining you, dear students, please listen this carefully. I am explaining you how to find out the factor of safety of this finite soil slope about this failure surface AD. We consider this failure surface in the graph sheet. We are going to find out the factor of safety of this finite soil slope about this failure surface AD. So first we calculate volume of this soil portion ABD. By knowing the unit weight gamma, we calculate the weight of the soil portion W. W is acting vertically downwards. Now on this failure surface AD, resolve this weight W into two components, normal component N, tangential component T. This normal component N is equal to W cos phi, cos alpha. With respect to horizontal, measure the angle made by the failure plane AD with respect to horizontal, take it as alpha. So this n is equal to W cos alpha, T is equal to W sin alpha. Since we know the value of W, we can calculate this value of n, we can calculate this value of T. So resolve this weight W into two components, normal component n, W cos alpha, tangential component T, W sin alpha. Then find out the shear strength of this soil. Check this tangential component T. This tangential component T is the shear force of the soil acting in downward direction. This shear force T causing the failure of this soil slope. So in this failure surface AD, this shear force T causing the failure of this soil slope. T is equal to W cos phi. Then find out the shear strength S of the soil. Shear strength S according to Coulomb equation. Here in Coulomb equation, this capital S is the shear strength force. It is either shear strength stress small s or the shear strength force capital S. Shear strength stress is equal to C plus sigma tan phi. That is the Coulomb equation to find out the shear strength stress. Small s is equal to quotient C plus sigma into tan phi. Sigma is the total or the effective normal stress. Then we have the another shear strength, that is the shear strength force S of the soil. The shear strength force S is equal to capital C total cohesion plus N normal force N into tan phi. That is this equation of shear strength S. S is equal to total cohesion C plus N normal force N into tan phi. That total cohesion C is equal to in soils, please listen everyone, in soils the cohesion C sometimes expressed as per meter length, that is small c. Small c is called the cohesion of soil per meter length. By conducting the field experiments, either the stand penetration test, cone penetration test, or the vein shear test, we can find out in the field the cohesion of soil per unit length small c. So that capital C total cohesion is equal to small c cohesion per unit length into length of the surface AD. Because this shear strength force is acting on the surface AD, because it is the failure surface. It is acting upward, resisting the failure, and T is acting downward, causing the failure. So this capital S is equal to capital C plus N into tan phi. So this C, capital C is equal to small c into the length of this failure surface AD. Since it is on the graph sheet, AD is on the graph sheet, we can measure this length AD in the graph sheet. You can calculate the total cohesion C. By knowing that small c cohesion per unit length from the field observation, we can find out that total cohesion C is equal to small c into length of this failure surface AD. N is known. N is equal to W cos phi into tan phi. Phi is the angle of shearing resistance. By conducting the field experiments, we can find out that phi value also from the field observations. We can find out that phi value also. So find out this shear strength force S. So the shear strength force S is equal to C plus N into tan phi. So in this procedure, for this plane AD, failure plane AD, for this failure plane AD, we know this tangential force T causing the failure. We know this shear strength force S resisting the failure. Then the factor of safety of finite side slope about this failure plane AD. This is the wedge failure plane. About this failure plane AD, the factor of safety of this finite side slope is equal to S divided by T. Since we know this value of S and value of T, we can find out the finite side slope factor of safety about this failure surface AD. So this is the procedure to find out the factor of safety of finite side slope in the wedge failure. Then we consider the another failure surface in the graph sheet. This is first failure surface EAD. I explained the procedure. Find out the weight of this soil portion ABD. Resolve that weight into two components. Normal component force N, tangential component force T. N is equal to W cos alpha. T is equal to W sin alpha. Find out the shear strength force S. S is equal to capital C plus N into tan phi. Find out the factor of safety of this finite soil slope about this failure surface EAD. Factor of safety is equal to S by T. Then take the another failure surface on the graph sheet like AE. Take the second failure surface on the graph sheet. Repeat the same process. Take the another failure surface AE. Find out the weight of the soil ABE W. Resolve that weight into two components N and T. Find out the shear strength S on the failure surface AE. Find out the factor of safety of this finite soil slope about the another failure surface. So like that, repeat this determination of factor of safety of finite soil slope with the different failure surfaces in this graph sheet. Then if you observe the factor of safeties among those different failure surfaces, the factor of safety of one failure surface is minimum. Among those different failure surfaces, the factor of safety of one failure surface is minimum. That is called the most critical failure surface of this finite soil slope. So in future, this finite soil slope is subjected to failure about that least factor of safety of the failure surface. So this is the procedure normally we adopted in the stability analysis of finite soil slopes in wedge failure. So this is entirely office work. In the office, the civil engineer prepares the plan on the graph sheet. Then by considering different failure planes in the graph sheet, he will calculate the factor of safety of the finite soil slope. Then on those factor of safeties, the minimum factor of safety is the critical failure surface of that particular structure. So this is the stability analysis of the finite soil slopes in the wedge failure. Then coming to the remaining procedures normally adopted in the stability analysis of finite soil slopes. We have number of methods to analyze the stability of finite soil slope. The first one is called Cullman's method. Next we have Taylor method. Next we have Swedish circle method. Next we have Bishop's method, like that. So we have different methods in the analysis of stability of the finite soil slope. This is also graphical method. It is also a paperwork. By sitting in the office, by using the graph sheet, by using this Cullman's method, we can find out the factor of safety of the finite soil slope. So I am going to explain what is this Cullman's graphical method. I am using the term graphical because we apply this Cullman's method on the graph sheet. So please remember, whenever we are discussing the stability of finite soil slope, it is totally the paperwork. It is totally on the graph sheet. By taking the embankment, canal or earth dam on the graph sheet, and by applying different methods, Cullman's method, Taylor method, Swedish circle method, Bishop's method, by using different methods, we are going to find out the factor of safety of the finite soil slopes. So all the methods I am going to discuss with you are totally graphical methods. But in some methods, we have some equations. I will tell you that later. By using those equations in the other methods, we can also check the stability of the finite soil slopes. So I am going to explain you the Cullman's method in the stability analysis of finite soil slope. It is important method. Please everyone follow this Cullman's procedure used in the stability analysis of finite soil slope. So check this diagram carefully. Please everyone check this diagram. So in the diagram, we have the finite side slope. Please everyone check this diagram. Here we have this finite side slope AB. This may be the finite side slope of an embankment or a canal or an earth dam. So this AB indicates the finite side slope. Let the vertical height of that finite side slope is h. This is inclined finite side slope AB. The vertical height of the finite side slope is h. Let this finite side slope AB with horizontal, making the angle I. I is the angle made by the finite side slope with horizontal. Then in the Cullman's method, please listen, in the Cullman's method, first we prepare this embankment on the graph sheet. We prepare this embankment including this side slope AB on the graph sheet. Take this entire diagram on the graph sheet. Then this side slope AB with the horizontal, making the angle I. Consider this failure plane AD, wedge failure plane. Since it is a plane failure surface, this indicates the wedge failure plane. Take that failure surface AD in the graph sheet. We are assuming this side slope AB subjected to wedge failure about this failure surface AD. This is a plane failure surface because here the failure is wedge failure. So take this failure surface AD in the graph sheet. Let this failure surface with horizontal, making the angle I. Let this failure surface with horizontal, making the angle I. So here in the diagram we have two angles. One is the angle made by side slope AB with horizontal I. Next one is angle made by the failure surface AD with horizontal alpha. Now consider this side portion in this ABD triangle. Take the side portion in the ABD triangle. In that triangle ABD, AB is the finite side slope. AD is the failure surface. So we consider the side portion in between the finite side slope AB and the failure surface AD. That side portion is called side wedge. We call this side portion as side wedge. Calculate the weight of the side wedge W. That W is the weight of the side wedge ABD W. Then you know that we can resolve this weight into components, normal component and tangential components. So please everyone check this diagram. So here between the side slope AB and the wedge failure surface AD, this portion of side is called side wedge. If this side slope subjected to failure, please listen, if this side slope AB subjected to failure about this failure surface AD, this side wedge portion is moving in downward direction. This side wedge in the failure situation is moving in downward direction. At the time of failure, the cohesion in this side wedge, at the time of failure, the cohesion in the side wedge is called mobilized cohesion, CM. So here you have this sign CM. Check the direction downwards. It indicates the failure condition of this side wedge. If and all this is side slope AB subjected to failure on the surface CD, on the surface AD, failure surface AD, at the instant of failure, the cohesion in this side wedge is called mobilized cohesion, CM. Since the side wedge is moving in downward direction, this mobilized cohesion is also moving in downward direction. Then on this surface AD, when this side wedge moving in downward direction, this surface AD applies a resistance force on this side wedge R. Check this third force. First I explain the weight of the side wedge ABD W. You know how to calculate this W. W is the weight of the side wedge. Calculate the area of this side wedge in the graph sheet. ABD, take the unit thickness, find out the volume. We know the gamma value from the field. So the weight W is equal to unit weight gamma into volume of the soil wedge. Then the second force is at the instant of failure of this soil wedge. The cohesion is developing in the soil wedge is called mobilized cohesion acting in the downward direction. This is unknown. Dear students, please focus this. This is unknown value, not known value. Nobody knows what is this CM value, but we have the procedure to find out this CM value. Check the direction carefully. CM is acting downward on the surface AD. Since this surface AD with horizontal making the angle alpha, this force CM, cohesion is a force, attraction force. This cohesion force with horizontal makes the angle alpha because it is acting on the surface CD with horizontal. The cohesion is making the angle alpha. Third one is R. R is called the resisting force from this failure surface AD on the soil wedge. I hope in engineering mechanics, please listen everyone. In engineering mechanics, you studied that reaction. Reaction is developing in the concept of engineering mechanics. I hope you know the reason for the reaction. Here I am not having the time to explain that. So listen that carefully. At the time of failure, the soil wedge is moving parallel to this surface AD. It is not moving perpendicular to surface AD. Since it is not moving perpendicular to surface AD, the surface AD applies the resistance on the soil wedge R. Now with this dotted line, this is called, this dotted line is perpendicular to surface AD. With this dotted line, this reaction will make some angle that is called angle of mobilized angle of internal friction phi m. We call this as phi m, the mobilized angle of internal friction. So in the diagram, we have totally three forces: W, weight of the soil wedge, ABD, the mobilized cohesion CM, unknown, the reaction R, unknown. Three forces are acting on the soil wedge. So at the time of failure, the soil wedge ABD subjected to three forces W, CM and R. Please everyone recollect the engineering mechanics basics. It is entirely the engineering mechanics. Please recollect the engineering mechanics. When three forces acting on the body, when the body is in equilibrium condition, the three forces forms the closed triangle. If three forces keeps the body in equilibrium condition, so here at the instant of failure, just at the time of failure, the soil wedge is in equilibrium condition because of this weight W, because of this cohesion CM, and because of this resistance R. Lamin's theorem, different students. Lamin's theorem is also three forces. That is very good. Lamin's theorem is applicable for three forces. F1 by sin alpha is equal to F2 by sin beta is equal to F3 by sin gamma. That is Lamin's theorem. That is also equilibrium of three forces. The other one is if three forces, this is the graphical equilibrium. Lamin's theorem is the mathematical equilibrium. The graphical equilibrium is due to three forces. If a body is in equilibrium condition, those three forces forms the closed triangle. From that also you can get the Lamin's theorem. So from that forced triangle, closed forced triangle, we can get the Lamin's theorem. Thank you for the response. At least one student knows that procedure. So please remember, otherwise recollect. You studied in the engineering mechanics, definitely the equilibrium condition of three forces acting on the body. So here this soil wedge is in the equilibrium condition because of W and CM and R. So these three forces will forms the closed triangle. Out of these three forces, we know the direction of W. W acting vertically downwards. We know the direction of W. We also know the magnitude of W because we can calculate the area of ABD in the graph sheet. You know the unit thickness 1 meter. You know the volume of the soil wedge V, and you know the unit weight from the field. So you can calculate this weight W. So here we know the direction of W vertically downwards and also the magnitude. The next one is Cm, unknown force. Third one is R, unknown force. Even though these two are unknown forces, you know the direction of Cm parallel to surface AD, making the angle alpha with horizontal. So in the graph sheet, you know this direction of CD downwards, but magnitude is unknown. You know the direction of this R because it is making the angle phi m with this normal. So in the graph sheet, you can measure this angle phi m because it is acting at that angle phi m. So here you know this direction of R, but magnitude is unknown. R is unknown. So please listen. Out of these three forces, one force W is known in magnitude as well as direction, and other force is known only in direction, and the third one is unknown force R. But the condition is these three forces are forming the closed force triangle. So prepare that force triangle. Prepare the force triangle by using W, Cm and R. So coming to this Cullman's procedure. So in the Cullman's procedure, we consider the soil slope AB, making an angle I with horizontal. Then we consider the failure surface AD in the graph sheet. That failure surface is making the angle alpha with horizontal. At the instant of failure, at the time of failure, about to failure, the cohesion force developing in the soil wedge in the downward direction on the surface AD, failure surface AD, that is called the mobilized cohesion force Cm. This is unknown. Then L is the length of the failure surface AD, H is the vertical height of the failure surface AB. H is the vertical height of that failure surface AB. Now I am going to explain how to find out the magnitude of the weight W. So check this diagram carefully. We are going to discuss the determination of the weight W mathematically. So in this diagram, take this 90 minus alpha, this angle. Since with horizontal, soil slope is making an angle I. Soil slope is making an angle I with horizontal. This remaining angle is 90 minus alpha. So in this 90 minus alpha, cos 90 minus alpha is equal to adjacent side. This is the height h of the soil slope. Adjacent side divided by hypotenuse is AB. So in this diagram, cos 90 minus alpha is equal to cos 90 minus alpha is equal to h divided by AB. Cos 90 minus alpha is sin alpha. So here cos 90 minus alpha is equal to adjacent side is h divided by hypotenuse is AB. Cos 90 minus alpha is equal to sin alpha, sin I. Cos 90 minus I is equal to sin I. So sin I is equal to h by AB. So the length AB of the soil slope is equal to h divided by sin I. So this is the length of soil slope AB, h divided by sin I. Then consider the another angle, that is BAD here. So check this angle BAD triangle. Here this angle BAD, take this side wedge. Take this side wedge. Here this angle. This angle is I minus alpha. So here this total angle is I and this angle is alpha. So this remaining angle is I minus alpha. Now observe this diagram ABD triangle. In this ABD triangle, one side is AB. Just now we calculated the length. The length of AB is h divided by sin I. Then here this angle is I minus alpha. Since we know this length AB and this angle I minus alpha, we can calculate the area of this triangle ABD. We have the formula in trigonometry. The area of the triangle ABD is equal to half into AB into AD into sine of angle at A. That is the angle at point at A, that is I minus alpha. So here this angle is I minus alpha. In the trigonometry, we have the area of triangle equation between the two sides of triangle. between the two sides AB and AD, between the two sides of triangle AB and AD, you know this angle. Then the area of this triangle ABD is equal to the side half into the side AB into side AD into sine of this angle between the two sides. That is the area of triangle formula. So this area of triangle ABD is equal to, this angle is I minus alpha between the sides AB and AD. So the area of this triangle ABD is equal to half into AB into AD into this angle I minus alpha. You know that the length of AD is L. That is the failure surface length L, and the length of AB h divided by sine I. So in this equation, the area of triangle ABD is half into AB into AD into the sine of angle between the side AB and AD, that is I minus alpha. Length of AB h by sine I. Just now we calculated here. AB length is equal to h by sine I. Length of AD is L. So the area of the triangle ABD half into h by sine I into L into sine I minus alpha. Then take the unit thickness. Take 1 meter thickness of that soil wedge ABD. So the volume of that soil wedge is equal to area into unit length. What is this area? Just now we calculated. Area is equal to half into side AB h by sine I, length AD L into sine I minus alpha. This is the volume of the soil wedge ABD per unit thickness. And take the unit weight of the soil is gamma. Bulk unit weight is gamma. Then the weight of the soil wedge W. The weight of the soil wedge W is equal to bulk unit weight gamma into volume. What is this volume? Half into h by sine I into L into sine I minus alpha. From the graph sheet, you know this h value, you know this L value, you know the I value and alpha value. All are known in the graph sheet. So you can calculate this volume V from the graph sheet. Then you know this bulk unit weight gamma from the field observation. So the weight of the soil wedge W is equal to half into gamma L h by sine I into sine I minus alpha. Gamma is known from the field observations, h is known from the graph, L is known from the graph, I and alpha known from the graph. So you can calculate the weight of this soil wedge ABD. Weight of the soil wedge ABD. Then just now I explained, when the soil wedge is about to failure on the surface CD in the downward direction, a cohesion force developing in the soil wedge. At the instant of failure of this soil wedge on the surface AD, a cohesion force developing in the soil wedge, that is called mobilized cohesion, capital Cm. That mobilized cohesion is equal to small cm, that is the mobilized cohesion per unit length into the length of the surface AD. You can also write this capital Cm, that is the total mobilized cohesion, capital Cm is equal to. So here the total mobilized cohesion force on the surface CD, on the surface AD, failure surface, capital Cm is equal to small cm into length of AD surface. Small cm is called the mobilized cohesion per unit length. L is the length of the surface AD. This is the total mobilized cohesion developing in the soil wedge at the instant of failure. So here this capital Cm is the total mobilized cohesion, unknown value. So don't confuse about this. This is unknown force, but it is developing in the soil wedge at the time of failure. So when the soil wedge is about to failure, at that instant of failure, a cohesion force developing in the soil wedge on the surface AD in the downward direction, that is called the mobilized cohesion of the soil slope Cm. That is equal to small cm into length of the failure surface AD. This small cm is called the mobilized cohesion per unit length. L is the length of the failure surface AD. Then coming to this diagram here, observe this diagram. Just in the previous diagram, I explained this CD Cm in the downward direction. So check this diagram. The first diagram, this is the mobilized cohesion force in the downward direction. So when this soil wedge, please everyone follow, when the soil wedge is about to failure on the surface CD, this soil wedge applies this mobilized cohesion in the downward direction. This is the force applied by the soil wedge on the surface AD. Since this soil wedge is applying the force Cm on the surface AD, the surface AD also applies the same force Cm on the soil wedge but in the upward direction. Because of Newton's third law, for every reaction there is equivalent opposite reaction. So at the time of failure, the soil wedge is moving downwards. At the time of downward movement, this soil wedge applies the force Cm on the surface AD. Then the surface AD applies the same force Cm on the soil wedge but in the upward direction. I am going to consider the free body diagram of the soil wedge ABD. In the engineering mechanics, you might have studied that free body diagram. So I am going to prepare the free body diagram of this soil wedge ABD. In the free body diagram, we must apply the forces acting on the soil wedge, not the forces applied by the soil wedge. Here this Cm is the force applied by soil wedge on the surface AD. Then the surface AD applies the same force Cm on the soil wedge but in the upward direction. So consider the free body diagram of the soil wedge ABD. So this is the free body diagram. So observe this carefully, students. This is the free body diagram of the soil wedge ABD. In the previous diagram, the soil wedge ABD applying the force Cm on the surface AD in downward direction. Then according to Newton's third law, the surface AD applies the same force Cm on the soil wedge AD in the upward direction. So in the free body diagram of the soil wedge, you must consider the forces acting on the soil wedge. So in this diagram, the force acting on the soil wedge or the weight of the soil wedge. Just now we discussed the equation to find out this weight W. From that equation, you can calculate this weight W. Then the second force is the force from this soil, this failure surface AD on the soil wedge, that is force Cm upward direction. The third force is reaction force. Since this soil wedge is not moving in the perpendicular direction, this surface AD applies the reaction on the soil wedge. This reaction R is from this soil wedge, is from this failure surface on the soil wedge. So three forces are acting on the soil wedge free body diagram. One is the weight of the soil wedge. Next one is the mobilized cohesion force Cm from this failure surface AD on the soil wedge in the upward direction. Third one is the reaction from this failure surface AD on the soil wedge in the upward direction, making the angle phi m with this normal. This normal is perpendicular to surface AD. So check this free body diagram of the soil wedge. Because of these three forces, because of W, because of Cm, because of R, due to these three forces, the soil wedge is in equilibrium condition. It remains in the same position in the structure because of these three forces. One is the weight of the soil wedge. Next one is the mobilized cohesion. Third one is the reaction. Since this soil wedge is in equilibrium condition due to these three forces forms the force triangle. Since we have three forces, these three forces forms the force triangle. That is a closed force triangle. Check that force triangle. Here you know the direction is vertically downwards. We know the magnitude. Only these two forces are unknown. Out of these two forces, Cm is known in the direction. It is acting upward parallel to surface AD, making the angle alpha with horizontal. So you know this direction of the force Cm. Now prepare that force triangle. So the soil wedge is in equilibrium condition due to this action of three forces. One is the weight of the soil wedge. Next one is the mobilized cohesion force Cm. Third one is the reaction. With perpendicular, the reaction is making the angle phi m. Since that soil bed is in equilibrium condition, the three forces will form the force triangle in the equilibrium condition. This is the force triangle. The force triangle of the three forces acting on the soil wedge. One is the weight of the soil wedge. We know the magnitude of weight W. You know the direction downwards. And from this point, please follow this procedure of preparing this force triangle. From this point, draw a straight line. Draw a straight line parallel to direction of CM. We don't know this magnitude of CM. This magnitude is unknown, but we know that direction of CM is known. So please check this diagram, everyone. This is a typical procedure, but entirely engineering mechanics. We know the magnitude and direction of W. We know the direction of CM, but we don't know the magnitude of CM, and we don't know the direction and magnitude of this R, because this phi m is unknown. Nobody knows this angle of phi m. It is also unknown value, but you know this R is in the upward direction. Direction upwards, but we don't need to know this angle phi. So here in the force triangle, the procedure is very important. First, prepare this W vertically downwards according to some scale. Assume that, listen students carefully, assume that this W is 100 kilonewton. Let this W is 100 kilonewton acting vertically downwards. Take the scale, 1 centimeter is equal to 10 kilonewton. Take the scale, 1 centimeter is equal to 10 kilonewton. So 100 kilonewton is equal to 10 centimeters length. Because the W is equal to 100 kilonewton, first take the scale, 1 centimeter is equal to 10 kilonewton. So this length is 10 centimeters. Draw that line first. Draw 10 centimeter vertical line. Then at this point, draw the another straight line. Draw the another straight line parallel to CM, because we know the direction of CM. CM is parallel to surface AD, making the angle alpha with horizontal. So draw the straight line parallel to direction of CM, long length. Then from this another point, draw this straight line. This is the direction of R. Draw this straight line from this other end. Then this straight line and this another straight line will meet at common point. These two straight lines are meeting at a point. Then this point, at this point, this length is the magnitude of CM. This length is the magnitude of CM, and this length is the magnitude of reaction R. So this is the procedure to prepare the force triangle in the Cullman's method. So in the Cullman's method, the soil wedge ABD is in the equilibrium condition. Under the action of three forces W, CM, and R. By using those three forces, prepare this force triangle. First, prepare the weight W on the white paper. Then from this end, draw the straight line parallel to force CM. Then from this other end, draw a straight line parallel to reaction R. These two straight lines will meet at a point. Then from this point to up to this point, the length is the mobilized quotient CM, and from this another point to up to this point, the length is the reaction R. So from this force triangle, we can calculate the magnitude of mobilized quotient CM. From the force triangle, we know this value of CM. I hope you remember in the stability of soil slopes, we discussed three factors of safeties. I explained three factors of safety in that concept of. So here I have the calculation. So by using this calculation also, we can calculate the mobilized quotient CM. I will explain this calculation of this force triangle in the next class. In the tomorrow class or on Monday class, I will explain. This is nothing but the Lamin's theorem, please. This triangle is nothing but the Lamin's theorem. So by using this triangle, you can find out this angle is alpha minus phi m. between the W and R, and between the W and CM this angle is 90 minus alpha, and between the CM and R this angle is 90 plus phi m. So I will explain about this forced triangle in the tomorrow's class. Okay students, with this I am going to stop this Cullman's method. Still we have the discussion in the Cullman's method. So please remember that basics of engineering mechanics. In this Cullman's method, we apply the basics of engineering mechanics. Three forces keeps the body equilibrium when the three forces forms this forced triangle. This is called the closed forced triangle. So here, by using this closed forced triangle, we can calculate this mobilized coefficient C, Cm, and from the field we know the natural coefficient C. The factor of safety of coefficient Fc is equal to natural coefficient by mobilized coefficient C by Cm. So by using that, you can calculate the factor of safety of the finite solid slope AP. So in the Monday class, I will again revise this Cullman's method, and at the time I will explain the another process to find out the factor of safety. So I am going to stop the today's class. We will continue this Cullman's method in the next class. Please leave from the class.